Information Extraction Meets the Semantic Web survey, which was a joint work with Jose Martinez and Ivan Lopez from Sinvestav in Mexico. So to first start with the context of the paper, this was a survey paper that was published at the Semantic Web Journal and was invited to be presented at this track. So the paper was published in 2020. So essentially we wanted to propose a survey or to look into how information extraction techniques were being used in the semantic web, and also how the semantic web was being used for information extraction in both directions. So the survey essentially is all of the works that somehow intersect between these two areas of the semantic web and the information extraction area. So in terms of the timeline and stats, I think it's important to give this context that, okay, we started work on this in 2016 when Jose visited Chile, where I work. We started to work on the survey at that stage to collect papers, to review them and so forth. It was submitted first to Semantic Web Journal in 2017, revised and accepted in 2018, and then official publication was in 2020. So the paper is quite large, 83 pages. We have 336 references. You have a query here if you want to grab the paper. I feel the context is important since the sorts of techniques that I will be presenting were up until about 2016 when we applied the survey methodology. So lots of things have changed in this area since, particularly with deep learning and so forth. I'll come back to that at the end of the talk. So with information extraction task, we identified three main tasks that we would like to focus on. Entity, extraction and linking. Extraction to identify in text mentions of entities, and then to link those mentions with knowledge graphs. Concepts, so more abstract ideas, not specific entities, but rather more abstract concepts, classes, whatever it might be, such as books, person, university. Again, extraction and linking with knowledge graphs, and relations, where we want to find binary or possibly n-ary relations between specific entities. For example, Donald Knuth here wrote Art of Computer Programming, and he worked in Stanford University. So the main focus of the survey was on text. However, there was also some discussion on semi-structured formats. So we'll talk a little bit very briefly at the end about that. So in terms of search methodology, we collected some keywords about entities, concepts, relations, and also about the semantic web. And then we took an OR over the entities or concepts or relations and semantic web. And this created a long list of searches that we applied in Google Scholar. And then we also expanded some of within the citation network paper, citing other papers. We tried to find other papers that were not necessarily captured by our search terms. So we see this is the number of papers that we considered, and this is the initial number of papers categorized by entities, concepts, and relations. And we see that there was 19,000 papers, which was a lot of papers to go through. After filtering by title, we got to about 429, and then after further looking into the abstract, 317, and then looking in detail at the paper, we discovered 89 focus papers. So there are also some related papers that discuss techniques, but these were papers describing techniques or systems that would fit the core survey. So in terms of entities, to start with, what did we find? Well, we found all these papers here relating to entities, and entity extraction and linking in the context of the semantic web. We discuss here year, knowledge-based matching, and so forth. So we break down different attributes of these systems and these techniques that were proposed. So to talk a little bit more about those techniques, typical entity extraction pipeline, what we start with is some sort of recognition process to identify the mentions of entities in text. Right? So here we see Knuth, Art of Computer Programming, Stanford being identified as entities. The next thing, there are two options for doing this. The first option that's very popular for this task is to apply named entity recognition, which has been studied in the natural language processing community during many, many years. So this will also identify certain types as well. So common ones being person, place, organization, but sometimes as well we could have works, we could have some other additional types. However, this is somewhat restrictive in that these named entity recognition tools typically only recognize a limited number of types of entities. Okay, so another option is to use the KG labels, the labels in the knowledge graphs of the entities, for example, Donald Knuth, whatever it might be, as a dictionary to see where we find some matches in the text. Yeah, so here we see Stanford, and if we search for Stanford in the labels of the knowledge graph, we might get two options: Stanford University and Stanford, the town or city. So in this case, we see that we have some ambiguity. We have Stanford the place and Stanford the university. Here we have Knuth, the minor planet. There's a minor planet that orbits the sun. That's called Knuth, 21656, and Donald Knuth. So what we would like to do next is, so if we apply this KG labels as a dictionary, we also solve the problem of candidate extraction directly. So we're associating already mentions directly with candidates. In the other case where we apply named entity recognition, once we've extracted these mentions of named entities, then we need to do some sort of search phase in order to generate the candidates. So as the next phase, what we would like to do in cases where we have multiple candidates in particular, and possibly also in cases where we have one candidate and we want to see if it's correct or not, is to apply disambiguation. So we really want to see if we can identify which of the entities in the knowledge graph are we speaking about in the setting. So this is an interesting task that gets beyond a little bit traditional natural language processing. So we could talk a bit more about that. So in order to disambiguate entities, there are lots of features that could be considered. For example, mention-based, where we use the text or the content of the mention, capitalization, how strong was the recognition. We could use keyword-based, so we could use the surrounding text of the mention and check its similarity with the text of the entity in Wikipedia, for example. We can apply graph-based, which I'll talk about in a second. We can apply some category-based features where we can use the domain of the text or using the categories of Wikipedia to understand if, loosely speaking, the entities in a certain part of text are related in that sense. Or also linguistic-based, so look at grammar, parts of speech, and so forth. So for graph-based entity disambiguation, which I said we'd return to, so the concept here, to illustrate, is to take these entities referring to the candidates in a particular part of text, and with the hypothesis that these should be somehow related because there seems to be some sort of relation if they appear together in a text. We can look at the knowledge graph and we can look at these entities and we can see what existing relations exist in our knowledge graph. And we'll see, for example, maybe that Donald Knuth has written this book and works at Stanford University, and Stanford University is based in a place called Stanford. But we might not actually see any connection to this minor planet. Okay, so in this case, we could say, okay, well, this seems to form somehow some coherent topic or related set of entities that could appear together in a text. And this one seems to be isolated, so maybe less likely to be relevant in the context of this text. So this is the basic idea. There are many, refinements on this with centrality and other measures to try to identify the more central graph cuts and so forth. But there are many works looking at this technique for disambiguation. So here we see a matrix in the paper. Again, don't have time to go into too much details here, but you can check out the paper. It breaks down for each system or each technique the features, the types of features it uses for disambiguation. Okay, so as a result of entity extraction and linking, what we will have is mentions in the text, positions of mentions in the text, and the entities are the IDs that refer to them in a knowledge graph, such as DBpedia, Freebase, Wikidata, Yago, maybe Wikipedia. Since there are links between many of these knowledge graphs, it's relatively straightforward to map from one knowledge graph to the other once we have the IDs for one of these knowledge graphs. So in terms of other topics covered by the paper, there's not enough time to discuss here. Ensemble systems, where we combine results from multiple systems, discussion about data sets used for training and testing, evaluation, and also some open questions and challenges. So what kinds of entities should we be linking? Should we also be linking, for example, Donald Knuth, but should we also be linking abstract concepts like person and so forth? How to improve multilingual support. There's a lot of emphasis on English, but not so much in other languages. And how can we optimize for specialized settings, for example, entity extraction from tweets, where there's a lot of abbreviations and very short text and so forth. So next up, we have concept extraction and linking. So this was perhaps the most diverse category in the in the paper, in the sense that there was no clear notion of concept extraction before. Rather, the people looked at terminology extraction, ontology building, key phrase extraction, and so forth, or topic modeling. So we tried to group these and extract some commonalities from these under the general idea of extracting higher level topics, concepts, and so forth. So a typical concept extraction pipeline involves, first of all, some sort of recognition of concepts or topics. So I would say topics is maybe a little bit different. So we'll maybe stick with concepts. So for concepts, we have, first of all, a recognition where we try to, for example, one option is to apply keyword extraction, where we identify certain keywords in the text that are related to the domain of interest. For example, in this case, it could be education. Another option is to do a more advanced key phrase extraction, where we actually extract n-grams or phrases with multiple words, for example, private research university. And in this option as well, we can sometimes induce a taxonomy or a hierarchy, for example, to say that a university is broader than a research university, which is broader than a private research university, based on head terms and modifying words, are also using Hurst patterns and so forth. Another important aspect of concept extraction in the pipeline is to apply some filtering. So in filtering, we'll often try to remove phrases that are not really phrases. For example, largest department is just, it's not a term of art in the same sense as one could recognize a private research university. It's a concept, largest department. One could argue is not so interesting. Termhood, which refers to basically the relevance to the domain of the keywords. Phrase depth, which refers to how deep in the document the terms appear, saying that concepts that appear early are likely to be more relevant to the domain under analysis. And finally, we have some representation step where we take what we've extracted and we use this as input for perhaps for ontology engineering, or we look to, for example, represent or taxonomy using something like SCOS or OWL or Lemon. So there are various ontologies for describing the outputs of these steps. So again, we have some other topics not discussed. Topic modeling is a little bit different in that the idea is to take a text and then extract the topic or concept of a text, something that can then be linked with the knowledge graph to say, this tweet here is related to this topic and described by the knowledge graph, for example. Also discuss data sets and evaluation in detail in the paper. And as some open questions, what about linking concepts? There hasn't been so much work on that. How would it be different from linking entities? And also, again, the challenge about multilinguality, how to support other languages besides English. So the third and final category we looked at was relation extraction and linking. So in this case, we want to find relations between specific entities. So here again is a list of all the papers. We see a bunch of papers ranging from 2013 to 2003, to 2017. So we see some of the features that we considered, which we'll talk a little bit more in detail about now. So a typical relation extraction pipeline, what we have, first of all, is some sort of entity recognition. So in the text, we want to, as we saw before, identify the entities that could be related according to the text. So we can apply first named entity recognition, which will just identify the mentions and some high-level types. A second option is just to apply entity linking, and that has the added benefit of actually giving us the IDs of the entities in the knowledge graph. So both options are applied in different settings or in different systems. Then we have what we could call relation recognition or the relation extraction itself, right? Where what we want to do is we want to identify, for example, that based on this text, we know that Knut wrote this book, Art of Computer Programming, and worked in Stanford. So the first type of relation we could consider are these sorts of binary relations, as we see here, where we just have two entities related by a named type of relation. So for this, a major trend at the time and still now is towards using distant supervision in the context of knowledge graphs. So the idea is we have some text and we have these two similar phrases in the text or sentences. And what we'll do is we'll identify the entities in both of these sentences from the knowledge graph. And then we can look to the knowledge graph to see what existing relations we have between these entities. So in our knowledge graph, we know that Turing wrote computability and lambda definability, and that Turing worked at Princeton. So based on this text, we could say, hey, maybe in other sentences that have the similar structure, the same relations apply. So in this case, we could, based on the similar sentence structure, actually propose these new relations that perhaps don't exist in our knowledge graph based on the structure of the sentences being similar here. So we take our existing knowledge from our knowledge graph, and we use that to find new relations in the text. Another option, rather than extracting binary relations, is to extract n-ary relations, where really we could say that this is not two binary relations, but rather an n-ary relation, because Canute wrote the book at Stanford, right? So this is somehow capturing new information not captured by the binary relation because it connects the three entities. So a typical way to extract n-ary relations is to apply some sort of parsing. In this case, we have a constituency parse where we have noun phrases, verbs, and so forth. We break down the text into small parts, and then we form a tree, a parse tree, which indicates higher level elements, are like verb phrases, prepositional phrases, arriving to the top level sentence structure. So based on this, we can then identify noun phrases, for example, we can write some expressions to capture noun phrases that are connected by verbs, what have you. We could also have more complex transformations in order to create n-ary relations. However, in n-ary relation, in this case, a 4, we have a relation of 4. The problem is that the fourth element could actually, in different settings, refer to a time, a place, a method. So to be more explicit, typically we use some sort of representation that would be similar to reification in graphs, where we create this new entity, which is the relation itself, and type it as right. And then we indicate the entities that are involved in this relation, and also some additional information, such as qualities or themes or places and so forth. So in terms of a typical relation extraction pipeline, the next thing we'd like to do is representation. So we'd like to represent this in a knowledge graph if it's not already. In the case of distance supervision, we'll actually get directly binary relations in the vocabulary of the knowledge graph. In other cases, we might need to apply an explicit linking process, not just of entities, but also of relations to identify these things in the knowledge graph. And finally, if we have n-ary relations like this, we may need to propose some sort of reification structure to represent this. So in terms of open questions and challenges, also to mention there's discussion in the paper about emerging relations or entities that are not in the KG. Some open questions and challenges: what types of relations should we extract? How do we extract n-ary relations in the native KG model, in the vocabulary used, and again, the multilingual setting? There's a lot of work in English, but not so much in other settings. So these are the three tasks we've discussed. As mentioned before, we focused on text. There is some discussion on semi-structured formats in the paper. Here you see some of the works, mainly for extracting from the web, from HTML pages, whatever it might be, from wikis and so forth. And that's pretty much the survey. But since the paper, there's been this explosion of deep learning, large language models, and so forth. So there's a question of, when I was invited to present this paper on behalf of the authors, I was wondering if what this would be, what I'm discussing here, is still applicable after the deep learning large language model knowledge graph boom. And I think that yes. So in terms of the paper scope, this is still relevant. We could have called it nowadays knowledge graph construction, for example. So the tasks are still very much applicable, and the techniques used are evolving quickly, but still relevant. Also comparing the presented techniques, the more traditional NLP style techniques, to things we see in deep learning. These techniques, more traditional techniques, are more transparent. They're easier to tweak. If we want to add a new pattern to capture a new case, we can do that, and better for the long tail with sparse data. But of course, if you have further thoughts on this, happy to discuss. So that's my presentation. Thank you for listening, and I'm happy to take any questions if there are. Okay, any questions? Any thoughts about the usefulness of this in the age of deep learning? Okay, I don't see any questions. I hope you enjoy. I believe the next session is starting at 2:30. Hope you enjoyed the rest of the conference. And thank you for attending the talk. Hope you found it interesting.